Hey, you guys missed my tour group. I apologize for running late. Welcome to Candy Labs, a new frontier in research and instrumentation. Right now, we're standing inside of the Instrument Repair Center, and if you guys want to go ahead and follow me over here. Out to your right-hand side, we have our office buildings, which house our cafeteria, our sleep lounges for staff that stay overnight with the labs, and we also have a gym. So we have an awful lot of stuff there, pretty much anything you could want. Over in the left wing of this building, we have labs. Unfortunately, we're not going to be able to look at all of them due to safety and security measures to keep you guys safe and keep our information secret. But we will be having a full tour of the entire facility, starting here in the Instrument Repair Center. And lucky you guys, today we are going to start with the IR spectrometer, or infrared spectrometer, which is the most important device to our research, and it just happens to be getting repaired today, so we're going to start there.
This is our infrared spectrometer. What it does is it measures the molecular vibrations in molecules. We have two different kinds of modules. One is reflection, one is transmission, depending on how your sample is. We can talk about that later. But first of all, the way it works is there's a helium neon light source in the back end, and it goes through several mirrors, a beam splitter, and interferometer, and several mirrors, and goes to this main chamber where we keep the samples. And then after it passes through the sample in a certain way, either by reflection or by transmission, it reaches this MCT detector, and MCT is in short for mercury cadmium telluride. And this one is really high sensitivity. Usually it needs to be cooled down by liquid nitrogen. And here we have the sample compartment where, I don't know if you can see from there, there's several mirrors that can reflect the beam to a sample sitting in there. So sample would sit in here, and I don't think I have the sample. Yeah, this is the sample holder. So we'll set the sample up. Usually in my case, it will be a gold film on silicon substrate, and I have molecules sitting on top of the gold. Of course, you can't see it by eyes, but I put it on top of this stage and slide it into this compartment, and then we can adjust the reflection angle on top. That's telling you right now it's hitting at about 85 degrees from the surface as a for the infrared light. And then, so this is the reflection chamber, and you hear this purging sound is because we want to remove carbon dioxide and water in the measurement, because especially water has a really strong absorption in a lot of wavelengths, and they have these really tiny spikes for broad range. So when we measure the samples, we want to make sure we get rid of the water first. So the gas that's purging into this is actually passing through the air line from the school, from the lab, and then goes through an air generator that removes the water and CO2. So when it goes in here, it's actually removing the water and CO2 in this whole chamber. All right,
With that, we've reached the end of our tour, but I have a special surprise in store for my favorite tour group. Now if you guys will step inside. Is there a restaurant around here? Oh, down the hall to the left across from room 337.
Earlier we were looking at that machine, and I was wondering what it actually measures.
The machine? Oh, are you referring to the IR machine?
Yeah, that one.
Well, the IR machine measures the vibrations of a diatomic molecule.
I thought that molecules only move locations.
Well, molecules can obviously translocate, but when exposed to infrared radiation, hence IR, they can actually bend or rotate.
molecules vibrate in the IR machine?
Well, everything needs energy to move. Cars, gasoline, people, food. In this case, radiation is our source of energy. Specifically, infrared radiation. When we apply this radiation to the molecule, it absorbs only part of the radiation and vibrates and becomes excited.
So what happens to the rest of the light that isn't absorbed?
The unabsorbed light passes all the way through the detector, which allows us to see which radiation is missing, because each molecule absorbs different radiation.
How does a molecule vibrate? I can't quite picture it in my head.
Well, I'm going to have to pass this question off to one of our head researchers, Dr. Oswald, because she's a leading expert in the field of vibrations and molecules, and I have another tour to go to, and I hope you guys enjoy the tour, and appreciate Candy Labs and the time you get to have with a head researcher. Thank you.
Hi guys. So let me see if I can explain this better.
Well, basically think of two balls. Each ball will represent an element. Let's say they are both hydrogens. Now if we add a spring in between the two balls, then the spring acts as a bond between the two elements, which we can call a diatomic molecule. Let's imagine that you pull the two balls far apart, and when you let go, the spring will oscillate back and forth. In a perfect world, where energy is completely conserved with this oscillation of the spring, it will keep on oscillating forever. But this is not the case here, because we have energy loss that goes from the system to the outer system. Energy loss due to heat and other transfers that might occur. But I won't go into the detail about that since it's a bit more complicated.
So what's so great about molecule vibrating then? I don't see why it's anything important.
As I was saying before, with this vibrating H2 molecule, the vibration is really important and it corresponds to an important concept of the harmonic oscillator.
Harmonic oscillator?
So the harmonic oscillator is basically like the system that I described, the H2 molecule. The molecule gets displaced from its original equilibrium position and then goes out and then back in and oscillates.
What's happening with the oscillation is that when the molecule is in the ground state, it has potential energy stored. When IR light hits the molecule, the potential energy converts to kinetic energy and the molecule starts to oscillate back and forth. This is when the molecule starts to get excited. Then, once all the potential energy is converted to kinetic energy, then it reaches a point for the kinetic energy to start decreasing and convert back to potential energy. This decrease in kinetic energy is when the molecule starts to go back to the ground state.
Does it matter what type of molecule?
It does matter. This is because each molecule has a different mass, and the frequency of vibration is dependent on that mass. The larger the mass, the harder it is for the molecule to vibrate fast compared to smaller molecules. Therefore, the frequency is smaller if the molecule is large, and the frequency is larger if the molecule has a smaller mass. But mass is not the only thing that makes it dependent. It also depends on the type of bond the molecule has. For simplicity, let's imagine the two balls connected with the spring again. Here we now need to consider the stiffness of the spring, which represents the bond strength. Therefore, each sample put into an IR machine requires a different frequency of light to be shown through it. If the spring is stiff, then the molecule will vibrate at a higher frequency, and if the spring is weak, it will vibrate at a lower frequency.
So, do you guys have any more questions?
No.
Well, thank you guys for showing so much interest in Candy Labs. We do a lot of important research here. And to show you what we really do, because we didn't get to see our labs today, we have a short little video to show you of what we further do at Candy Labs.
Here at Candy Labs, we study hypothetical reactions, and that lets us maybe as chemists, more generally speaking, develop chemistry in a rational design type approach. I'm a member of the Candy laboratory staff here, and my group and I explore how chemistry occurs by way of computational methods using theory and modeling to really understand at the atomistic level how catalysis in particular works. So we study chemistry in silico, means that rather than working at a bench top and having to worry about getting dirty and working with nasty chemicals, we actually sit at a computer and we write equations based on physics that tell us how atoms interact with one another to do chemistry, and then we use that to model chemistry that otherwise would have to be done on the bench top. This lets us do a couple of things that are difficult to do in a wet lab.
And here at Chemie Lab, I research about basic scientific questions about biosensors. Here at Chemie Lab,
Defining the new frontier.
chemical research and instrumentation.